If you're a Java developer, chances are you've used a hash set. I mean, we all have, right? It's fast, it's simple, and it makes sure you don't have any duplicates. But have you ever really stopped and wondered, how does it actually work? What's the secret sauce that makes it so efficient? Well, today, we're going to pull back the curtain and see exactly what's going on under the hood. All right, here's our game plan. First, we'll cover the basics, what a hash set promises to do. Then, we get to the good part. We'll reveal its biggest secret, which, spoiler alert, involves another collection you definitely know. After that, we'll dig into how it actually keeps everything unique, look at the performance trade-offs, because there's always a trade-off, and then wrap it all up with the key takeaways you'll actually use. Okay, first things first. Before we dive deep into the internals, let's just make sure we're all on the same page. From a developer's point of view, what is a hash set even for? What's its one simple promise? So here's the simple textbook definition. At its core, a hash set makes one huge guarantee. Every single thing you put in it will be unique, no duplicates allowed, period. It also lets you have one and only one null element. And here's the kicker. It makes zero promises about order. If you add A, then B, then C, don't be surprised if they come out in a totally different sequence. Order is just not its thing. So this slide really sums it up. You've got that uniqueness guarantee, which is ironclad. You can have that one null value. The insertion order is totally out the window, and that's the trade-off you make for its main benefit, raw speed. And we're talking incredible speed, constant time or O of 1 performance for adding, removing, and checking if something's in there. That means it takes pretty much the same amount of time whether you have 10 items or 10 million. And of course, like most of these collections, it is not thread safe right out of the box. So we know what it does, but how? How does it pull off that speed and uniqueness? This, my friends, is where it gets really, really interesting. It's time to peek under the hood. And there it is, the big secret. A hash set isn't some magical new data structure built from the ground up. Nope. It's actually a really clever wrapper. Just an abstraction built right on top of another Java workhorse, the HashMap. And once you understand this one fact, everything else about a hash set just clicks into place. And you don't have to take my word for it. The proof is right there in the source code. This one single line of code tells the entire story. When you call the .add method on your hash set, all it's doing behind the scenes is turning around and calling .put on its private internal HashMap. That's it. That's the whole trick. So you might be thinking, wait a minute, a HashMap stores key value pairs. Where's the value? Well, the answer is, it doesn't matter. The elements you add to the hash cert, those become the keys in that internal HashMap. And the value? It's just a single static dummy object that's the same for every single entry. The hash set only cares about the keys because a HashMap won't allow duplicate keys. Okay, so that leads us to the next logical question, right? If the hash set is just piggybacking on a HashMap's keys, then how does the HashMap enforce uniqueness? Well, it all comes down to one of the most fundamental contracts in all of Java. The critical dance between the hashCode and equals methods. It's this really clever two-step process. First, when you try to add an object, Java calls its hashCode method. It gets back a number, an integer, and uses that number to very quickly find a spot in memory, a bucket, where that object should live. Now, for step 2, what if there's already something in that bucket? That's what we call a hash collision. At that point, and only at that point, Java starts calling the equals method. It compares your new object to everything already in that bucket. If equals comes back false for all of them, then congratulations, your object is unique and it gets added. And this is a perfect example of how Java keeps getting smarter. Before Java 8, if a bunch of objects all ended up in the same bucket, they were just chained together in a simple linked list. And if you had a really bad hash function, finding something could slow to a crawl. But since Java 8, we've got a huge improvement. If one of those lists gets too long, Java automatically converts it into a self-balancing binary tree. All you really need to know is that this dramatically improves the worst-case search time, making the whole thing much more reliable and predictable. Okay, but all this amazing speed, it doesn't come for free. Nothing ever does, right? As is so often the case in computer science, the trade-off is memory. So let's talk about the real price of all this performance. But first, let's just remember what we're buying with all that memory. We're getting that glorious, beautiful, constant time performance on average. For adding, removing, and checking for items, the time it takes doesn't really grow as the set gets bigger. That's the huge win. That's what we're paying for. And here's the bill. Even before you add a single element to it, just creating an empty hash set can take up around 144 bytes of memory. That's the fixed overhead just to get the structure in place. including that internal hash map. And it doesn't stop there. For every single item you add, you're tacking on another 32 bytes of overhead. Why? Because your item gets wrapped inside a HashMap entry object, which needs space to store metadata like the hashcode and pointers. So if you have a hash set with, say, 10,000 items, you're looking at over 300 kilobytes of just overhead before you even count the size of your actual data. Now, the good news is you do have a little bit of control. Think of these as two performance tuning knobs. The initial capacity is just how many buckets the HashMap starts with. If you know you're going to have a ton of items, setting this high from the start can save you from a bunch of costly resize operations later. Then there's the load factor, which is basically a threshold that says when the map is this % full, it's time to resize. The default of 0.75 is usually a pretty good balance. Okay, let's pull all of this together. What's the bottom line? What are the most important things for us as developers to remember when we reach for a hash set? This pretty much says it all. In the pro column, it's crazy fast, and it guarantees everything inside is unique. Can't beat that. But in the con column, it's a bit of a memory hog, and you completely give up any control over the order of your elements. Knowing this trade-off is absolutely crucial for deciding if it's the right tool for your specific problem. And this quote just nails the whole concept. When you try to add a duplicate item, the HashMap's put method might overwrite the old value with the new one, but it doesn't change the key itself. And since the hash set is only interested in that collection of keys, from its perspective, nothing has changed. The set remains the same. So after all this, we're left with one final question that really ties everything together. Is it fair to just say that a hash set is really nothing more than a hash map where we've decided to completely ignore the values? And the answer is a resounding yes. It's honestly one of the most elegant examples of clever code reuse you'll find in the Java collections framework.